Today we're going to be talking about modeling and optimization. And here are the steps to modeling and optimization that I had written on the website above the videos. Make sure you have these written down in your notes. So first we want to draw a picture of the situation, and that's going to help you, especially if a picture isn't given. Then you write an equation that is to be maximized or minimized, and this is going to be in one variable. Make sure that you only have one variable in there. Find the domain restrictions. This is the one I sometimes forget. I'm going to work really hard throughout these lessons to make sure that I am showing you guys this. Then we take the derivative to find the max or min. We justify the answer by our first derivative or second derivative test. And then lastly, does your answer make sense? Okay, this first example is an example of a figure inscribed under a curve. So a rectangle has two lower corners on the x-axis, two upper corners on the curve y equals 6x squared. For all those rectangles, what are the dimensions of the one with the largest area? So draw a picture of what we have. That's our first step. So let's draw a picture. Okay, we know that graph is a parabola that opens down, that has y-intercepts of positive and negative 4, and then has a vertex at 0, 16. Your picture doesn't have to be super accurate, but gives you an idea. Now we have two lower corners on the x-axis. I don't know where they're going to be, but then two of them are up on our curve. And then I need to find the dimensions of the largest area. Now area is length times width. Let's figure out what our width is. So the width here from 0 over to this value would be x. So the whole width would be 2x, because I need this in one variable. Now our height would be our function value because it's a y number. So that would be 16 minus x squared. So multiplying that through, we get 32x minus 2x to the third. Okay, we've written our equation in one variable. We need to figure out our domain restrictions on x. Well, the largest that x can be is from negative 4 to 4. Because if I go larger than 4, your rectangle is going to be outside your curve, and that wouldn't make any sense. Now we take our derivative. So we find the derivative of area because I'm trying to maximize or minimize this. So that would be 32 minus 6x squared. Set that derivative equal to 0. Set your factor. Equal to 0. Solving for that, we get plus or minus 4 over root 3. Now I get the same thing because our rectangle is going to be symmetric. So I'm just going to worry about the positive version. And instead of using the first derivative test, I'm going to use the second derivative test, because the second derivative test actually is a lot more efficient in this case. So we find our second derivative, and our second derivative is negative 12x. I evaluate that second derivative at the critical points from our first derivative, which would be a negative number. So I don't really even care what it is. It's some negative number, which is less than 0. So if your second derivative is negative, evaluated at the critical points of our first derivative, then we know we have a max. We have a max by the second derivative test. Okay, make sure you're answering the question. For all such rectangles, what are the dimensions? Well, we know our x value is 4 over square root of 3. Actually, no, that's not our value. Our value is twice that. So our value is actually 8 root 3, okay, because it's twice as big. And now I plug in this 4 root 3 into the function. So to get my y coordinate out, and simplifying that out, we get a 32 over 3. So a 32 over 3. So these are our dimensions of our rectangle. Again, I had to multiply our x coordinate by 2 because our bottom base was twice as long. Today we're going to be talking about an optimization problem where we have a box. So an open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares from equal sides from the four corners and bending up the sides. What size should the square be to obtain a box with a maximum volume? So let's write an equation for volume. Volume is length times width times height. So our volume in this case, the height is x, which is this length here, which is what I'm cutting out. The width is 30 minus 2x. I started with 30, but I've cut out x from both sides, so that's 30 minus 2x. And our length is 16 minus 2x. Now our domain restriction is 0 is less than x is less than 8. Because if I cut more than 8 inches from our width, I couldn't cut 9 inches from one side and 9 inches from the other side because I only have 16 inches that I'm able to cut, and I need to cut equal lengths from both sides. Okay, foiling that out. I'm not going to bore you guys with FOIL because that's an Algebra 1 skill. Now we take our derivative of volume. Now set that derivative equal to 0. I'm going to factor out a common factor of 4. And then I'm going to factor that guy even more. Okay, so now set each one of those factors equal to 0. So we get, in this case, 10/3 and 12. But let's look at this. 12 isn't in our domain, so 10/3 is the only one that's in our domain. So now we need to show this now we need to prove that this is a maximum or a minimum. So on my little number line chart, I'm going to put 0, I'm going to put 8 because those are my domain restrictions. Luckily you realize 10/3 happens in between. And we're looking at the sign of our derivative. So if I plug in, say, 1 into our derivative, if I plug in 1, I get a negative times a negative, which is a positive. So I'm increasing. And then something between 10/3 and 8. I'm going to plug in 4. Here I get a positive, but here I get a negative, so I'm negative, so I'm decreasing. So I change from, my derivative, I apologize, changes from positive to negative. So therefore we have a max at x equals 10/3 because v prime of x changes from positive to negative. Okay, so again, let's make sure that we are giving our dimensions. So what size should the square be? Oh, what size should the square be? So that's all I have to do. I don't have to give dimensions. We just have to give that our square is 10/3, and let's make sure you give me units, inches by 10/3 inches, since it is a square. Our next example is we're talking about distance. So we're finding all points on a curve, y equals square root of x, from 0 to 3. So that gives me my domain restriction that are closest to and the greatest distance from the point to 0. Okay, so again, let's draw a picture of what this means for us. Square root of x, the one-winged bird. So I want to know when the distance from any point on my curve between 0 and 3, which is the point of x, root x, and the point 2, 0, is both the closest to and greatest distance. So we're trying to maximize and minimize that segment. So our distance, use our distance formula. Square root of the difference of the x's squared plus the difference of the y's squared. Simplifying that out and multiplying everything out, okay, now there's a trick with this one. At this point I would have you guys finding the derivative. Now if we maximize or minimize distance, that's really the same thing as maximizing or minimizing the distance squared. So basically, I can look at this distance squared function and look at maximizing what's underneath the radical and minimizing what's underneath the radical, because the radical is just going to make it slightly less. So I'm going to look at what the derivative of that inside piece is, and that's 2x minus 3. I set that derivative equal to 0. And I solve for x equals 3/2. So that's my critical point. So again, let's use our first derivative test. And let's look at essentially what the distance squared is. From 0 to 3/2 to 3 is. So if I'm looking at 1, I need to look and see whether or not our distance squared is positive or negative. So that's going to be negative. So we're decreasing. Then we start increasing. So I'm decreasing, then increasing. So it appears I might have a minimum at 3/2, but they gave me a set interval. And this goes back to the very first section we did, where we're finding the maximum or minimum on a set interval. So what we actually need to find is we actually need to find our distance function. Now the original distance function evaluated at 0, evaluated at our critical point, and evaluated at the other endpoint. So when you evaluate these, Distance evaluated at 0 ends up being 2. Our distance evaluated at 3/2. Now I'm plugging this into this distance function. We get the square root of 7/2. And then when I plug in 3, I get 2. So now you need to look and see which one of those is a maximum, which one of those is a minimum. This decimal approximation is 1.323. So therefore, this is a max. And this is also a max, since those ended up being the same value. And this was a min. Okay, so then final points on the curve. Okay, so my point on my curve where my max is is 0, 2, and the point of 3√3. The point for our min was 3/2, and then the square root of 3/2. Now what I'm actually doing is I took these critical points, the two endpoints, and our critical point in the middle, and I plugged those back into the original function because I needed to find the points on the curve. This is an inscribed example where we have one figure inscribed in another. So we need to find the dimensions and volume of a right circular cylinder of maximum volume. So we're maximizing the volume of a cylinder inscribed in a sphere with radius 14 centimeters. So we need to find a picture. So I have a sphere, and inside of that sphere, I'm going to inscribe a cylinder. Okay, so, and we're maximizing the volume of our cylinder. So volume of a cylinder is pi r squared h. Okay, so we're maximizing that. So r is the radius of the top, that's what r is, and height is this whole distance. The only thing that they give us is they give us, from the center of our sphere, the radius of our cylinder to be 14. So we have a right triangle here. So that is half of our height. The reason I need that is I need this volume equation in one variable. I know that r squared plus h squared over 4 equals 14 squared, which is 196. So since I have an r squared in this volume equation, I'm going to solve for r squared in this other equation. Okay, so now volume equals pi r squared h. R squared was 196 minus h squared over 4. Then I simplify that. And I'm going to distribute the pi in and the h in. Okay, so that's our volume equation. Now think about what we have to range between. R is between 0 and 14, and H also has to be greater than 0, but H is going to actually be less than twice of 14, which is 28. Okay, let's find the derivative of our volume function in relation to H to find our maximum. So we have 196 pi minus 3 pi h squared over 4. I set that equal to 0. So h squared, simplifying all that out, is 784 over 3, which means that h is going to be plus or minus root 784 over root 3, which works out to be 28 over root 3. Now I need to determine that, or verify that that's a maximum. So let's find the second derivative and use our second derivative test. So our second derivative ends up being negative 3 pi h over 2. I evaluate that second derivative at my critical point in the first derivative. And I don't really even care what that is. I just need to know whether that's positive or negative. That is going to be less than 0, which means I'm concave down, which means my critical point is a max. Max at h equals 28 over root 3, which in your calculator rounded to 3 decimal places is that. Okay, and it's a max by the second derivative test. Because f double prime of our h value was less than 0, where v prime of h equaled 0. So I have my h. I need to know the dimensions and volume. So once I know h, I plug back into our r squared formula. I plug in h there, and I got in my calculator 11.431 centimeters. And then I plug into my volume equation r squared and h, and when I plugged that in, I got a volume of 6,636.166 centimeters cubed. And again, make sure that you are rounding to 3 decimal places. This is what I call a rotational example. So I have a right triangle whose hypotenuse is 20 meters long, is revolved around one of its legs to generate a right circular cone. Find the radius, height, and volume of the cone with the greatest volume that can be made. Okay, so we have a right triangle whose hypotenuse is root 20, and it's revolved around its leg to generate a right circular cone. So what if I took and I revolved this around and we got a cone? So we have a right angle there, that's the radius of our base, and that's our height. I want to find the greatest volume of this cone. So we're maximizing volume of a cone, which is 1/3 pi r squared h. Okay, so let's look at this. I need this in one variable. What's the relationship between h, r, and root 20? Well, we know r squared plus h squared is going to equal root 20 squared. Since our volume equation involves r squared, let's solve for r squared. So substituting that now in, volume is equal to pi over 3 r squared h. Okay, simplifying that out. Okay, now let's take our derivative. And think of pi over 3 as just a constant. So you can leave that out in front. So taking my derivative, my first derivative is going to be 20 minus 3h squared. And then, remember, we set that equal to 0. And I set each one of my factors equal to 0, so 20 minus 3h squared equal to 0. I solve for h, which happens to be the square root of 20 over 3, which as a decimal is 2.582. Now I need to verify that that is a maximum or a minimum. I really need to verify it's a maximum because we're looking for the greatest volume. Again, the second derivative test is going to be the easiest one here. So let's look at our second derivative. Our second derivative is pi over 3 times by negative 6h. I need to evaluate our second derivative at our critical point. Okay, so then I don't even really care what the value is. I just know, since I'm plugging a positive in, that's going to be less than 0. So therefore, we're going to have a max. Okay, so now that I know that that's a max, I know that my h, we already found, was square root of 20 over 3. So now when I plug that into our r squared minus equals 20 minus h squared equation, r ends up being the square root of 40 over 3. And remember, let's get some units in here. This is meters. So then plugging that in for volume, we get pi over 3. R squared is 40 over 3. And h is the square root of 20 over 3. Now, I'm personally okay if you do that. Math Excel, they might want you to round this to 3 decimal places. So it's just a matter of putting these values in your calculator and finding out exactly what they are. Today we're going to be talking about maximum profit. And this is a good economics example. If you end up taking business calculus in college, you're going to be using this a lot. So if you're of a business degree, you're going to probably be taking business calculus. Okay, so we have a revenue equation from selling X amount of items. The cost is the cost of producing them, and our profit is from selling X items. Now the marginal revenue, marginal cost, and marginal profit are the derivatives of each one of those functions. Okay, marginal profit occurs at the production level, in which the marginal revenue, so when the derivative of revenue equals the derivative of cost. So let's look at why that is for a super quick second. Profit is this equation. If we want to maximize that equation, we take our derivative. So remember, our derivative is what we call the revenue, or the marginal of each one of these functions. Remember, when we're trying to maximize or minimize, you set the derivative equal to 0. So now if I add the C prime, which is our marginal cost, over to the other side, that is why when we're finding the maximum profit, we have our marginal cost equaling the marginal revenue. So an example of this now. Suppose we have a revenue function and a cost function measured in thousands of units. That's going to be key. Is there a production level that maximizes? So I need to maximize my profit. Remember, we find our maximum profit when we take and we set the derivative of our revenue equal to the derivative of the cost. So what is derivative of revenue? That's going to be 20x to the negative 1/2. Revenue derivative of cost is going to be equal to, so we set those two quantities equal because I'm looking for maximum profit. So we have when 1 over the square root of x equals x over 1. So I have that when x to the 3/2, I apologize, 3/2 equals 1. So that's when x equals 1. So now let's use our second derivative test. So our second derivative, remember our derivative really is revenue, the derivative of revenue minus the derivative of cost. So therefore our second derivative is going to be this. That was a 20x, so that's why it's negative 20. I was already taking my derivative in my head. Okay, so now when I plug in 1 there, I have negative 10 minus 20. That's going to be less than 0. So therefore, we're going to have a maximum. So by our second derivative test, max profit occurs for 1,000 units. Okay, because remember, x was measured in thousands of units. So that is one of our maximizing profit examples.